In the previous videos, we have been looking at massless springs. So now in this question, let us look at a massive spring. So the question is, determine the time period of the system of mass m attached with a spring of mass ms, and we are given that the mass of spring is much smaller in comparison to the mass of the block, and the spring has spring constant K. So if we draw the diagram, we have a block of mass m, spring of mass ms, and spring constant K. We need to find out the time period for such a system. Now let us solve this question. So we are given that since mass of spring is much smaller in comparison to the mass of the block, we can safely assume that the spring will stretch uniformly along its length. So we can have a uniform mass dense distribution and uniform stretch along the length of the spring. So let us consider that the length of the spring is L, length of spring be L. So for this case, then we will have the linear mass density or mass per unit length this is going to be equal to mass of the spring over the length of the spring. Now if we let us draw this spring again. So if we consider an element, let us consider an element of the spring, the element of length ds. So this length is ds. So the mass of this element is going to be equal to dm will be the mass density times the length of the element. Now let us displace the block that we have. So we have the block over here, and let us displace it from its equilibrium by x, and this distance from the wall is s, and the length of this element is ds. Now the displacement of the element of the spring, so if we displace the block by x amount, so displacement of block is x. So this would give that displacement of element of spring would be equal to S over L times X, because we have assumed that the mass of the spring is much less than the mass of the block. So this would lead to uniform stretch in the spring. So from that we find that the displacement of the element at the distance S from the fixed end would be S by L times X. Now the velocity of this element of the particular element in consideration will be simply the displacement, rate of change of displacement by time. So S and L are constants, so it will be dx over dt. Now the kinetic energy of this element, we can find out the kinetic energy of element. Kinetic energy of element, this will be equal to half, so kinetic energy is half mv squared, so m over here of the element is dm, and let us give these some names. So this is displacement of element of spring, so it is x of s, this is v of s, so this is half dm v of s squared. So and this is ke of the element, so we can substitute the values of dm and vs to give us the kinetic energy of the element to be equal to half times ms over L ts times s over L dx by dt whole squared. So simplifying this expression gives us ms over 2L cubed times dx by dt whole squared s squared ds. So this is kinetic energy of the element. So total kinetic energy of the spring, so total kinetic energy of spring would be found by adding up the kinetic energies of each of the elements, or essentially integrating. So total kinetic energy would be integrating this expression. So total kinetic energy Ke of spring, of the entire spring, will be integrating this kinetic energy of element from 0 to L, integrating over the length of the spring. So let us just put in the values. So let us solve this integration. It is a simple integral. So L cube gets cancelled. This gives us total kinetic energy of the spring is equal to half ms by 3 dx over dt squared. So now total kinetic energy of the whole system, that is spring plus the block, would be, so total kinetic energy of the system is kinetic energy of the spring plus kinetic energy of the block. So kinetic energy of spring we just evaluated is the following. And kinetic energy of the block is nothing but half m v squared, v being dx over dt. So this gives us the following expression. So if we rewrite, so dx over dt is v, so v is equal to dx over dt. Now we see that this is like the effective mass of the system. So effective mass of the system is m plus ms over 3. This is the effective mass. Effective mass of the system, and hence the time period is given by 2 pi square root effective mass over k, which is nothing but 2 pi square root. We just found out the effective mass over here, m plus ms over 3 divided by k. This is the time period that we wanted to find out. So this is the time period in the case of a massive spring with mass. So for spring with mass, but the mass of the spring is much smaller in comparison to the mass of the block attached to the spring. So in such a case we get the following time period of the system.